get started. If I do go into a coughing fit, take that as an opportunity to ask questions. I will still be listening. So today we're going to talk about valuation uncertainty in the age of robot learning. You've all seen really cool stuff come out of a lot of different companies. I don't need to harp on this, but in the context of all that cool stuff, we also have failures, right? The top two videos are from Pi, of the Pi 0 or Pi 0.5 models failing, and the bottom two are from TRI. We also have failures, big surprise. Cool. So given the existence of these imperfect models, we have the trustworthy learning under uncertainty group within the large behavior model division at TRI. I co-lead this group with Dr. Haruki Nishimura, and here's a quick sampling of a few of our papers and videos. I'm going to zoom in to a few of these as well. So what do we care about? Three different things that we call our core research thrusts: policy evaluation, failure detection mitigation, and active learning. What do those things mean? In the evaluation setting, we're really thinking about how do we characterize success and failure of these policies. In the failure detection side of things, we want to find these failures quickly and then gracefully recover from. And lastly, in the active learning domain, we want to think about how can we learn from these failures and then adapt so that we can have more robust policies. Very recent direction that sort of lives in between failure detection and active learning is data curation and selection. If we have enough time, I will very quickly spotlight the recent work in that space. So this is the plan for the talk. You won't be surprised. And for those of you keeping time, you can see where I am. So let's start with policy evaluation. So this kind of plot is something that we see in a lot of robot learning papers, right? We have some success rates, bars, baselines, our new method. Great. Real world evaluation is expensive. So we have to ask questions like, how many rollouts do we need? Is 10 rollouts enough, right? Is it okay to say, hey, this baseline got 8 out of 10 success rate and we got 9 out of 10 success rate. We're better. Yay. Is that good enough? The other bit about robot evaluation that's really difficult is that there's a lot of nuance going on, right? There's different platforms, environments, tasks, camera angles, et cetera, et cetera. The example I have going here, the top one, it's a towel folding task. You want to fold it twice, put it away. Top one is in distribution. Everything works great. It's happy. Second one, we turn the lights down. It's completely broken. Third one is a towel it's never seen during training. And it's completely fine, right? And looking at these, I can probably hypothesize in hindsight, okay, well, maybe color jitter is making this work, or maybe something else like the green glare is really making it out of distribution. I can backwards reason through this. But forwards thinking, it's really hard to predict what all of these nuances are going to be, right? There's a lot of black box magic happening. So what do we do currently within the evaluation space in robotics? Very often you have that first plot, right? That table. You select 7 successes out of 10 trials and you report, hey, I have a 70% success rate. What if we want something just a little bit more nuanced, right? What if we want to say something like, we are 95% confident that our success rate is at least, say, whatever, 46%. And we have some looseness on this lower confidence bound. That is the average excess length. Okay, so we want to do something just a little bit more nuanced. This paper got accepted to REL. It was an internship 2 summers ago. The paper is led out by Joe Vincent, and it was recently presented at Itkina. So what Joe wanted to do is to find a lower confidence bound that optimizes 3 trade-offs. The first is coverage probability. That's this blue bit. It's the idea that whatever lower bound we come up with is actually a lower bound on the true success rate probability that we don't know. Okay, so that's step 1. Step 2 is the excess length of the lower confidence bound. Saying 0% success rate is my lower bound will always be true, but it will not be useful to you, right? So we want a minimum excess length here. And the last bit is we don't have a lot of human time to do a lot of rollouts, so we want to do as few rollouts as possible. So what does this look like in practice? We have this pour ice from mug task in two different out of distribution settings. In the first one, it's a benign setting. We added some distractors. It still works fine. There are 38 successes out of 50 trials, and the lower confidence bound is 64%, which, from the empirical success rate of 76%, pretty close. Then in the harmful case, we added a distractor the same color as the mug, and everything broke. So we got 4 successes out of 50 trials, and the lower confidence bound is essentially 0%. So if you're a company thinking about, do I want to deploy either one of these policies, you have this information to work with. The 0% one, probably not useful for anything. The 64% one, if you have imprecise tasks where you have some room for error, maybe that's good enough. You can also use this confidence interval-based method to actually compare different policies. So Joe took a table from RT2. They were comparing against BC1, and he concluded, yes, actually this comparison, they're all separable statistically, and this comparison is fair. RT2 is better than BC1 across each one of these 3 tasks. Can we do better? So with the confidence interval-based methods, we're optimizing 3 different things. The true success rate of your baseline, the true success rate of your new policy, and whether your new policy is better than the baseline. Okay, so 3 different things we're optimizing. And what happens if our confidence intervals overlap? Are we doomed? Does this mean that the new policy is not better than the baseline policy? Well, there was a paper in 2016 that actually debunked this and said, no, you're not doomed. Doesn't necessarily mean that the 2 policies are not separable if the confidence intervals overlap. And this is where A/B testing comes in, because A/B testing only optimizes the comparison, right? So is the new policy better than the baseline policy? And in that is more. So A/B testing, a very common method of that is batch testing, and even more specifically, Barnard's test. The problem with batch testing is that you need to know N, which is the number of rollouts that you're going to run ahead of time. If you don't, if you add rollouts later, you can invalidate your false positive rate guarantee. You don't want to do that. So keep the guarantees. Maybe you decide, I have 100 rollouts that I'd like to start with, and see how it goes. And I compare 2 policies. And at the end of the day, we actually found that we don't have enough data to make a conclusion. But I have a few more hours of rollouts that I can do. Unfortunately, I have to throw out all of this and start again, right? So that's wasted time. What if, in the flip side, I choose the maximum amount of time budget that I have to do these rollouts? I decide I have time to do 500 rollouts. I'm going to do all of them. And we get separation. Great, but we may have wasted 250 rollouts if that decision could have been made earlier, right? So it's this guess and check. This is where David's paper from his internship last summer actually comes in. This was presented on Sunday here at RSS. And the method that David came up with is called sequential testing for efficient policy comparison, or STEP. The goal for this method is to control the false positive rate for the entire decision-making process, and then also terminate in as few trials as possible. This is the saving time thing. So what this looks like is we start running rollouts. At every point, we have a decision to continue or to stop, and we continue until we have a decision, right? In this case, the new policy is better than the old. So zooming in a little bit more, this becomes a multi-objective constrained optimization problem, and it actually reduces down to a linear program, which is great. So the decision set that we're thinking about is first the null hypothesis, the baseline is better than our new policy, the alternative hypothesis that the new policy is better than the baseline, And the last option, we don't have enough data. What we then want to do is build a decision rule from the information we have, like the number of successes we've observed for each policy so far, and the number of samples, and map that to this decision set. This reduces down to this optimization problem where we want to be fast. We want to minimize the expected number of rollouts needed to make the decision. We want to be correct in the sense that we want our true positive rate to be as high as possible, highest statistical power. And we want to be safe. So whatever false positive rate we decided we're okay with, we'd like to stick to that. One nuance here is we still need an Nmax. And you might be thinking, this is counterintuitive to everything you've said so far, right? If we still need to decide on the maximum number of rollouts that we're going to run, what's the point? Well, actually, empirically, we found that we're pretty robust to this number Nmax. And I'll show that in a second. Okay, first example. This is a coffee spill cleanup task. We have an in distribution setting with an in distribution towel here, out of distribution towel here. Very big gap in empirical success rate performance. And the time to separate these, the number of rollouts to separate these two policies is 8 trials. Okay, so pretty quickly, our Nmax budget was 50 here. A common problem in robotics is choosing a checkpoint. Validation loss is not always a great indicator of what checkpoint will perform better in the real world. So maybe we're running some rollouts to decide this. In this case, there are two checkpoints that have about the same MSE. And here we have a slightly smaller empirical success rate gap, 92% versus 56% between these two checkpoints. And the number of trials it takes is 19. Okay, in simpler env, we have an even smaller gap here, right? So you're getting to smaller and smaller gaps between the empirical success rates. Here we're looking at 40% versus 56%. And now we have a higher Nmax for this purpose, 500 trials, and we finish in 131 trials, right? So thinking about that first example that I gave, we can decide on this really large 500 number, but we actually don't end up using all of it, which is nice. So how robust are we to the actual Nmax? Before I showed this checkpoint example with the 50 Nmax. Now it's 200, so 4 times. And we lost 2 trials. So it's 21 trials to decision versus 19 trials to decision. If we further up this to 500 for the Nmax, we lose another 2 trials, right? So thinking about the 50 Nmax to 500, that's a 10x, and we've lost 4 trials total. Overall, I would be okay with that. So you're pretty safe to go for a larger Nmax and be a little bit more conservative and lose a couple trials here and there, but you're definitely not going through all the way to 500, which you would with a batch method potentially. Cool. So method for sequential policy comparison. Why should you care? Minimize number of rollouts to policy separation. And the most important bit really here, the insight is this allows you to peek at the data, right? You can make decisions while you're evaluating. You can say, okay, we have separation now. We don't need to do the rest of this rollout set. You can quit now. Yeah. If you'd like to check out the paper, it's here. And with that, let's move on to failure detection mitigation. So far, we've been talking about batched rollouts, right? That's the evaluation setting. Now we're thinking about within the rollout, right? Maybe we're trying to do pick and place, and instead of going down, we start going up, not towards the object. We want to identify that kind of situation, and we want to flag it. So why do we need failure detection? I probably don't need to explain that in the OOD workshop, but the obvious one is safety and monitoring for the system. The slightly less obvious one is targeted data collection and recovery, going towards learning and adapting from these failure modes to actually robustify and improve model performance. The not that hot take, but kind of, is regardless of how much data we have, we're always going to have a long tail. Maybe that long tail is going to get smaller and smaller and smaller in probability, but it's always going to be there. And it is our job and our responsibility to think about that long tail and to make sure that when those failures do happen, we have ways to safely and gracefully recover from those failures. So why is failure detection difficult? This is an extremely simple environment from RoboMimic, right? But look at how many different failure points there are in this super simple, clean environment, right? So a lot of failure variations. The other bit that's hard is figuring out what signals are actually useful for this, right? Is it action conditions? Is it observations? Is it something else entirely? What is indicative of failure? So this paper was also presented at RSS on Sunday. This was the work of my intern, Chen Su, thinking about failure detection for imitation learning policy. So Chen came up with this method called fail detect, failure analysis and imitation learning, detecting failures without failure data. It's a two-stage approach. In stage one, we take whatever input your imitation learning policy takes, images. We have a feature extractor, and then we have robot states. All this goes into an observation vector, a score network, and output a scalar score. Right? One very important bit here is that the feature extractor, ResNet, clip, whatever it is that we take, is trained in the loop with your policy. Right? So when you have a diffusion policy or a flow matching policy, whatever it is, the feature extractor it uses is the same feature extractor and the same weights that we use for failure detection. Why is that important? Well, we don't care about the pixels. We don't care about detecting out of distribution in the pixel space. We care about the changes in the policy that cause failure. So in this example, we have an in distribution failure where it's a towel it's seen before, but it fails anyway. Let me run it again. And then this out of distribution towel works fine, right? That's what we care about. We want this to be successful, this out of distribution bit, and this to be a failure. And so that's why it's important to use these observations that are policy aware. Stage two is, okay, we have the scalar score that's hopefully reflective of successes and failures, but we need a threshold, right? We need to know when we can flag failure for this runtime monitor. And for that, we use something called conformal prediction. I'm sure a lot of you have heard of it. We need some successful rollouts in the environment that we'd like to test in, and then we can build this temporally aware threshold. And then the method becomes pretty simple, right? We get a score at every time step, and when this score exceeds the threshold, that's when we flag failure. Okay. Assumptions, I've kind of alluded to a lot of these, but just to make them super explicit, we need the training demonstrations from your imitation learning policy. We need the learned feature outputs from your policy network. And we need successful rollouts set aside for calibration. And just to highlight this one point is for this paper, I wanted to focus on only using successful data. And the reason it actually goes back to that first slide on the failure detection, why is it hard? There's so many failure modes, and I don't want to overfit the failure modes that I can name or I have in my data. So I choose to be a little bit more conservative in this first round and focus on modeling the successful distribution. And everything outside of that successful distribution is going to be a failure. The calibration allows us to moderate that a little bit, but that's what we wanted to stick to. And I wanted to see how far we could take this. Okay, Chen did a lot of work. He tried out a lot of different methods. He looked at post hoc methods, thinking about smoothness, some previous papers. He looked at a lot of learning-based out of distribution techniques, and he ended up coming up with the method that appears empirically to be most robust out of what we've tried. So this method, it's actually kind of straightforward. He set up a flow matching formulation that goes between the observation encodings, right? The thing out of your ResNet or your clip, to a standard Gaussian latent space. And then you can actually rearrange this equation to get this, so that when you get a new embedding, you can embed that through the network. You can get your Z in this flow matching formulation. If you assume a standard Gaussian there, you can get a log likelihood, and that ends up being your learned failure score. So the higher this L2 norm of your encoding, of your observation, encoding, there's two encodings there, the lower the likelihood, the higher the chance of failure. The second stage is score calibration. I mentioned this, we use temporally aware conformal prediction band. We need the successful rollouts in the environment to calibrate this method. The benefits are it's distribution free, score agnostic, and it controls the false positive rate. So what you can see here, I'm going to flip, and we have the band. And what you're really looking for are these red spikes, which are failures, coming out of that band, whereas the majority of the successes, which are blue, staying within that band. Okay, videos. This is in simulation, RoboMimic, so fairly straightforward tasks. Put the square on the thing, transport, and the hang tool task. So looking at the failures, these are a bit fast, so I will slow them down / play them a few times. So what happens in this one is as soon as it tries to grip, it slips and we flag failure. At the transport, it's kind of actually funny what happens here. So if you watch it again, it throws out the lid. And when it throws out the lid, things become visually weird for the policy. And so we're able to actually predict failure before the actual failure moment happens. And this is just on incident because that's the failure, right? It couldn't pick up the hammer and hand it over. The lid was not part of the success criteria. But it's kind of neat that we can identify this weirdness in the visual space that caused the policy to fail. This one's pretty straightforward, tries to hang something, misses, we flag failure. Great. Okay, hardware. On that fold towel task, we consider two different scenarios. The first scenario is you have an annoying human trying to mess with your robot. So after the first fold, it moves the towel. It's possible to succeed, but less frequent. The second scenario was actually a crumpled towel to start with and an out of distribution distractor, that blue spatula that's being blocked by this arm right now. So what do the failures look like? This is the interrupt case where the human interrupts. That's the first fold. Human is annoying here. Robot starts jittering. Tries to pick up that end, messes up the fold, and we call failure. Here, tries to unfurl the towel. Starts jittering again. That's a good sign things are not doing great. Missed that end. That failed at the fold, and we call failure. Last set of examples I'll show is for that cleanup spill task. This is with an in-distribution towel and out-of-distribution towel. So for the in-distribution case, it missed the mug. It was supposed to try and put the mug away. And now it's freaking out. Fail detect flags it. The second case is actually kind of interesting, so I'm going to pause it. It missed picking up the towel, and it was going to shove its gripper into the coffee. So this is an excellent case of where we need an automated failure detection system, unless you want to have the person like be stressed out and hitting fail all the time, because this could cause damage to the hardware. This cuts off because our robot teachers did not want to damage the hardware. Okay, yeah, so with that, this is fail detect. 2 stages. We learn our score, calibrate our threshold, and then we have a runtime failure monitor. The takeaways here, this model, this setup is flexible, right? We don't care. You can switch out the score as long as it's more or less useful to discriminate between failures and successes. You can use any score you like. If you have something better than conformal prediction for thresholding, you could do that. What I found really exciting and unusual is that the performance in simulation and in hardware was about the same. It was about 75% accuracy in both settings, pretty much no matter what we try. Yeah, that's new to me. For most of the other methods, everything was flip-flopping. In one task, one method would be better. In a different task, a different method would be better. If you'd like to check out the paper, it's here. I think I will try to get through data curation very quickly, but in the last 2 minutes, I will just highlight this much more new effort for us that I'm really excited about. So this is a paper led by Krisija and Rohan Sinha, who are both here. And it's a collaboration with Jeanette Bug, Marco Pavone, and Rika Antonova. And it actually was just presented at the RoboVal workshop. So for data curation and selection, we still have our set of demonstrations, right? The demonstration data we know and love. Then we train our policy, and we end up with rollouts in whatever deployment environment we have. And maybe we have an expected return. For us, we're mostly thinking about success rates, successes and failures. What data curation selection likes to do, or wants to do, is go back from, hey, this rollout failed. What data contributed to that? And can we rank this data so that we can maximize our success rate in whatever deployment environment? I'm not going to go into any of the details for this work. This is the high-level insight. We want to predictively answer counterfactual questions about the training data. So the question is, what if I remove this demonstration from my data set? What is the change in expected reward or expected return that you're going to get? And the bigger this difference, the more important your demonstration towards the success of your policy. So this is a high level of what this method looks like. You might have demonstrations that are low quality, high quality. They have good strategies, bad strategies, etc. You train your policy, your BC policy, you get an expected return, and then you want to predict this counterfactual question with something called influence functions, which comes from the data attribution community. And this results in a ranking, and you can delete your lowest ranked data points. So I'll show 3 examples of this. This first task called Figure 8, it's a mixed quality data set, right? So we have good demos, bad demos. If we just blindly train our policy on all of the demonstrations, ends up not doing so great, 36% success rate, kind of fails. If we filter 66% of the data, so 2/3 of the data, we end up with a policy that succeeds 72% of the time. This is based off 25 rollouts. Okay, second task. What if we have 2 strategies? So for this recycle bin situation, there were 2 strategies. One is push it, another one is pick it up and move it underneath. And during the deployment stage, we played a trick on the robot. We added weight to the box, right? And when we added weight to the box, it became out of distribution. And for whatever reason, the strategy that the policy just naturally preferred was this pushing one. And it failed. It actually got 0% in the 25 rollouts. If you filter, again, it figures out this pick strategy by ranking the demos. And then it results in 84% success rate. So that's a pretty significant jump. The last example I'll show is the spurious correlation example. So there are 2 settings. One has a dark background, one has a light background. And there are also 2 scenarios that the demonstrator was dealing with. The task is to pull a book out. That book might have a book on top of it. In that case, you want to pull vertically so the other book doesn't fall out. If the book is by itself, you want to pull towards yourself. That's more natural, easier to. But there was a spurious correlation. So whenever there was a dark background, the book was pulled vertically. And when there was a light background, it was pulled this way. So in real life, when you switch up these backgrounds, it goes for the wrong strategy. right? Because it's a light background. And with 50% of the data filtered, it actually figures out the correct strategy so that the book does not fall out. Okay, so the idea here, yep, I'm basically done. So the idea is we're connecting policy evaluation to the data set, requires relatively few rollouts, flexible to data curation selection. I didn't have time to talk about the selection, but you can check out the paper to learn more. Thank you.
As we take questions, it would be great if all of our lightning talk presenters can start lining up. There's a door to the side over there. I'll open it and you can sort of pile into the hallway there. You should all have a spreadsheet that David sent out earlier today with the ordering, but I have it here too. So I'll just walk by and like help you all get in line. And then David will set up the presentation and then Masha can take some questions.
Yeah, question over there.
Yeah, since in the fail detect paper, the failure detection is based on out of distribution data. Is there
Sorry, I can't hear the question, so could we have quiet in the back?
yeah, is there the potential that we actually mistakenly classify those out of distribution successes as failure because of that?
Out of distribute, yes, completely. And it's kind of a subjective thing, right? Because if the out of distribution policy is actually jittery and it's slow, right? Then is that a success? Maybe, but it's kind of up to you. And that's where the calibration comes in. You can calibrate in your out of distribution environment, and then you can sort of adjust that gap. Yeah. And we tried both things in the paper.
Hi, thank you.
Sorry, you're gonna have to speak over.
I'm gonna yell, sorry. I like the talk very much, thank you. I thought it was really interesting how you could detect failures without failure data. I'm wondering, like the classical failure field is called fault detection, isolation, and recovery, I think, or identification recovery. So I understand how you can do like the first steps of that, like diagnosis, there's a problem, shut down or something, but how do you view like this failure-less data-less architectures extending to those later stages of like identification and recovery?
So recovery is actually something we're thinking about now. We're thinking exactly that about how can we use the score to recover. The other bit is it's not yet predictive. So there was that moment where it was kind of predictive, but that's more by accident or by construction of what was visually happening in the scene. Thinking about how to predict this failure is a whole other problem. And that would help with the mitigation as well. Sure. I don't know, duke it out, maybe in the back.
Thank you so much for the talk. My question on your work on stopping early for once the results separate. Do you ever want to see how much they separate by, and is that information lost if you stop early as soon as they separate?
You want to take this one?
Oh, sorry, I was actually thinking
It's okay. It's okay. No, not as much. We're really trying to make a binary decision in terms of when we have separation. And as soon as we have separation, we want to stop as quickly as possible. How much separation is kind of not irrelevant, but kind of in this case. When you're thinking about how much, you might actually want that confidence interval approach where you're measuring the absolute performance, right? It does make a difference if, for example, it's 90 versus 70% versus 20 versus 40% or something like that, right?
Let's thank the speaker again.
Thank you.